Bismillahirrahmanirrahim. Assalamu alaikum. Welcome to the lecture 9 of digital signal processing. I am Muhammad Atif and my registration number is 16T108. Today I will explain fast Fourier transform using 2-point DFT. As we know that the fast Fourier transform is another method to calculate the DFT. It is more efficient and reduces the computation cost. The FFT is based on complex DFT. Here complex means that the specific type of mathematics is used. So starting from the example, I have I have signal x of n is equal to 1 minus 1 2 0 1 minus 1 1 and 3, and in which I have 0 index is at 1. This explains the index matching between input sequence, and this explains the bit reversal process. First, the input data with indices 0 1 2 3 4 5 6 7 are split into two parts. The first part contains the even indices 0 2 4 6, and the second part contains the odd indices 1 3 5 and 7. This further splits into two parts. First one even indices and the second one odd indices, and the second half with indices 1 3 5 7 likewise split into these two indices, like even and odd. The bit pattern of the output data indices are just the respective reversed bit patterns. Here we see that these are the reverse of input bits. This block diagram shows how I apply the 2-point DFT at these indexes. So when by using the formula x of k equal to e of n plus omega kn into O of n, I calculate these points where omega kn is either 1 or minus 1. It is 1 at 0 and minus 1 at pi. So after apply 2-point DFT, I get 2 0 3 1 minus 2 0 3 and minus 3, and at this point I apply the 4-point DFT by applying the same formula, but here omega n is calculated by the circle by dividing it into 4 different parts. Here omega 0 4 equal to 1 1 4 equal to minus j, and the omega 2 4 minus 1, and omega 3 4 equal to j. By applying 4-point DFT, I get 5 minus j minus 1 j 1 3j minus 5 and minus 3j, and at this point I apply the 8-point DFT to get the final result, and omega is calculated by dividing the circle into 8 respective parts. By applying the 8-point DFT, I get 6 2.12 plus j minus 1 plus 5j at x of 2 minus 2.12 plus j 3.12 at x of 3, and at x of 4 I have 4. And after this conjugate start, x of 5 is the conjugate of x of 3, and x of 6 is conjugate of x of 2, and x of 7 is the conjugate of x of 1. Now I apply inverse fast Fourier transform to see this is its effect on original signal. This explains the index matching, and this explains the reverse bit as I explained earlier. So by applying 2-point DFT at these points, I get these points 10 2 minus 2 10j minus 2j 4.5 plus 4.2j 2j minus 4.2 plus 4.2j, and applying 4 point DFT at these I get these points, and by applying 8 point DFT at these points I get the final results. And this is the multiple of 8 of regional signal. By comparing them with regional signal, comparing it with original signal, we get to know that this is the multiple of 8 of regional signal. Thank you, and this is it for today.